Hey everyone, I'm Niels Provos. I've been working on security for 30 years now. And in fact, I found my first security vulnerability in February 1997, back when vulnerabilities were still being discovered by humans. This has completely changed these days. As you're all aware, we are currently facing an avalanche of AI-identified security vulnerabilities. And in this talk, the day after the 0 days, I will be discussing how these vulnerabilities are being found and what we can do about it. And I have to tell you already, the answer is not gonna be just patching. So let's go back a month. This was when Anthropic made the news about their new Mythos model. They were trying to create a model that was much, much better at writing code. But in their evaluation as a responsible company, they were trying to figure out whether there were sort of any other consequences of releasing this model. They identified that Mythos was also very, very good at identifying vulnerabilities and writing exploits about them. And they published their findings in a Red Team report on April 7th this year. And their key highlighted vulnerability was a 27-year-old vulnerability in OpenBSD in the TCP SAC implementation. An adversary with the right packet could kernel panic any OpenBSD machine connected to the internet. Well, as it turns out, the TCP SAC implementation was committed in November 1998 by myself. So I guess now you can also say that I have been contributing security vulnerabilities for the last 30 years. But rightly, the industry has been discussing this a lot. This was discussed in the press. That's made it to the highest levels of the government in the US because people are worried about what are we going to do if all of these security vulnerabilities are now being found so easily. And in fact, Anthropic is sitting on over 600 vulnerabilities and they still haven't figured out how to upstream all of them because the validation just is so time intensive. However, all of this made me wonder, what can anybody who doesn't have access to such an embargoed model have to in order to find vulnerabilities? And a while ago, I created my Iron Curtain Secure Agent Runtime. And it turns out, building the right scaffolding on top of it, I was able to replicate some of the Mythos findings using available models, such as Opus or Sonnet 4.6, and even open weight models like GLM 5.1. And in fact, the ability to find vulnerabilities with available models has been around for quite a few months, and adversaries with the right scaffolding and harness we're already able to do this. Now, with the Iron Curtain workflow as open source, any defender can leverage this too and find vulnerabilities. However, the assumption that we have to make now is vulnerabilities are easily detectable. But why has this been a problem before? Why has this not been the case sort of the very first moment that LLMs were being released? And so now we have to talk about some of the limitations. When I talk about LLMs, I'm talking about a large language model that is being harnessed inside of an agent loop such as Claude Code or Codex or Goose. And if you listen to Nicholas Carlini's talk at Unprompted, he had the slide where he talked about the challenge that frontier models have with long horizon prompt following. And he basically said that at the moment, most of these models sort of can roughly stay on task for about 15 hours when compared to a human. But after that, they just drift and they don't complete what they were being asked to do. The other problem is also context recognition. As the context of the model fills up, its performance gets worse and worse, and it gets worse and worse at reasoning about the data that it has seen already. But even more challenging is the fact that all of these models are trained to complete. And that means that, with reinforcement learning, they don't get to do hundreds or thousands of turns. They're being trained to complete after 50 turns. And when these models end up seeing that the goal is almost in sight, they just go for it. whereas the prompt might have said, no, you can't do that. You have to do other things first. And while with Mythos, Nicholas Carlini was basically able to say, hey, here is a file, assume that you are in a capture the flag competition and just go for it. That is not possible with lesser models. While Mythos is sort of really good to then take this single prompt and sort of read the surrounding source code and hypothesize and then ultimately find the vulnerabilities and build an exploit to exercise this is not something that is possible with smaller or less sophisticated models at the moment. However, the process of finding a new vulnerability is actually a fairly mechanical process, and we can decompose it into many different steps. And it usually starts by, let's read the source code, let's understand the entry points, let's identify sort of how all these functions in the source code chain together, and then since we have been doing vulnerability research for so many years, we have a very good understanding of the patterns of vulnerabilities. And so we can look at the source code and basically say, hey, this looks like a suspicious pattern in this function, or there's something suspicious about how these two functions call each other. And then we can build some code to exercise the area of code where we suspect the vulnerability might hide. And I call this a harness. And this harness, may use code coverage, it may use fuzzing. The idea is we create a situation where with the right inputs, we can trigger the vulnerability or not. And if we trigger the vulnerability, we just have proven that there is a problem. And if we don't trigger it, then we have shown that the vulnerability has been disproved. But while we can decompose this into these predictable steps, as I mentioned before, there is a problem with these LLMs. They can't follow these prompts over long time horizons. And what I found out is that if we use finite state machines, and I built this on top of Iron Curtain as a finite state machine workflow, this actually ends up changing. Because now all of a sudden we can force these LLMs and the agent loops to go through very prescribed transitions. And one good example here is design and coding loop, where you might say, here is an area I want to design for. You ask the agent to create the design, and then in that state machine, that agent goes to a design review, and the design reviewer looks at the design. It might find some flaws, gives it back to the design agents, or the design might get approved, and then a human gets to look at it and can say, yeah, this is ready for implementation, or it needs to go back to the designer because there's still a problem with it. If you just gave this to an agent loop without any of the finite state machine harness around it, the agent loop might just say, hey, I just approved this design. Let's just go and implement it. And the benefit here is the finite state machine doesn't allow that. And so the decomposed workflow that I mentioned before, how we find vulnerabilities, that is now something that we can precisely implement as such a finite state machine. And the idea here is that I have an orchestrator. The orchestrator is basically just responsible for keeping a journal of what happened. It's an append-only journal. And the first step in finding a vulnerability is to go to an analyze state. And think here about a Docker container with Claude Code or Goose that basically gets the task from the human and then starts looking at the source code. It will look at the entry points. It will do pattern matching on potential vulnerabilities and create a long list of hypotheses of, there might be a vulnerability here, there might be an integer overflow there might be an array with a bounce check missing, and so forth. And then the orchestrator says, great, we now have 15 hypotheses. Let's take one of them and test it out. And it will now go to a harness design and build state that basically creates a reproducible scaffolding that allows us to execute code in the vicinity of where we suspect the vulnerability might lie. Once that harness has been validated, the orchestrator will give it to a discover state. And in the discover state, the agent loop will basically try as hard as it can to exercise and trigger the vulnerability that the hypothesis found. And if it's successful, it goes to the triage state. The triage state is a very prescripted way of now turning this discovered vulnerability into something that's reportable. It will validate all of the findings. It will make sure that the source code is attributed correctly. It may validate the fix, and it will also create a CVSS rating for the severity of this problem. And then once all hypotheses have been discharged, there is a conclude state, and the conclude state basically writes up a human consumable report. In all of this, there is the opportunity for the agent to say, hey, I'm super confused. I don't know what to do anymore. This now needs to go to a human for further guidance, and then the human can give instructions to the orchestrator on what to do. And it turns out this works incredibly well. Just the other day, I was running this against an open source project, and this workflow ran for 3 days without interruption and stayed completely on task. So now you might wonder, what is it that this workflow actually finds and produces? And in my experience, no matter what code base I pointed this workflow at, it always found something that was reportable. And so I've been working on disclosure with a number of open source maintainers. And one of the things that I've seen is they're inundated with these AI slop reports. And they're on their own. They are not part of a $1 trillion company. They don't have any special access to any special models. They have to figure this out on their own. And they're just really overwhelmed. So it was important that for the findings that I report, that we really have execution-based proof. This cannot just be something where an LLM or an agent loop said, oh yeah, there's a vulnerability here. We actually need to get to a place where we have an input, a proof of concept that executes the vulnerability. And then we need to have artifacts that demonstrate to the maintainers that this vulnerability really exists. And this may be an ASAN trace, this may be a segmentation fault, this may be information disclosure to bypass ASLR and so forth. So my goal here is not to create weaponized exploits. My goal is to demonstrate exploitation primitives to prove to these maintainers that there really is something there. So we are not trying to build a new $20 million zero-click exploit against iPhones, but we need to give something to the maintainers that is easy for them to ingest and that demonstrates to them that there's a real vulnerability that needs to be taken care of. Because otherwise they just get inundated and they are unable to keep up with all the bug reports. Let's talk about what we actually ended up finding. I pointed this at numerous open source media libraries. I'm not disclosing any names here. The vulnerabilities have all been patched, but there have not been sort of releases or any advisories made public yet. One was a vulnerability was very interesting. It was an image processing library, and it was due to an integer truncation. I got a heap out of bounds read and write. And the read actually provided an ASLR bypass. ASLR stands for address space layout randomization, and it basically allows you to read pointers that then give you an idea where functions might be. And you can utilize that knowledge in a heap out of bounds write to maybe overwrite function pointers or those kind of things. So that was a fairly severe vulnerability. It has been in that source code for 18 years. Another vulnerability was in a video codec library, and it was an integer wrap, only reproducible on 32-bit builds, but it provided a heap out of bounds write primitive. Another one, also an image processing library, was a resource exhaustion denial of service vulnerability, and it basically created a 25,000 amplification in memory based on the input size. And I'm usually not a big fan of reporting resource exhaustion vulnerabilities, but this one seemed meaningful enough to report it up. However, more importantly, since the workflow generates so many hypotheses, it's also really, really important that we get proof when an hypothesis was ruled out. And the workflow provides that too. It gives line coverage, it says seeds, how many fuzzing runs were done, what kind of checks prevented the vulnerability from being exploitable, and so forth. So, very predictable. I find vulnerabilities in every single piece of open source code I have pointed this at yet. And it begs the question, if you're a CISO, what is it that you are supposed to do with that? And many CISOs have vulnerability management programs. These are programs to triage vulnerabilities and get them fixed. And a tempting answer may just be, I will create a really, really top-notch vulnerability management program, and we will just take care of all of the vulnerabilities in our production environment. And I have to tell you, if that is your approach to dealing with this AI bugmageddon, that is a failing strategy. The environment has completely shifted on us. In the past, you might have had enough time to patch because it took longer to find these vulnerabilities than to actually address them. But these days, this has completely changed. And even worse, so many companies are now using AI to write code. And I can tell you from my own experience, the models at the moment produce terrible code. I've yet to see an example where I would say this was really top-notch code. And in fact, sort of through review cycles, there's not a single review cycle where the review cycle doesn't find problems with the AI written code. So you can expect that thanks to vibe coding, we'll be seeing way more vulnerabilities in the future. And these vulnerabilities will outpace your ability to manage them through a vulnerability management program. So that then begs the question, well, what can we do instead? And the answer is, stop just chasing the bugs. You have to actually build infrastructure that eliminates the attack surface. And I call this security invariants. These are properties that you put into your infrastructure that are consistently enforced, and they do not require any ongoing human judgment. And while you might still have vulnerabilities in your environment, these security invariants make it so that an attacker can no longer get their kill chain to complete. And they are really the way in which you create a top-notch security program. So let's talk a little bit more about what that actually means. 2 years ago, I did an analysis of data breaches. And I found that just 3 security invariants are sufficient to materially mitigate 65% of these breaches. And these invariants are a hardware second factor for authentication, egress control, and positive execution control. So let's go into this in a little bit more detail. By hardware second factor, I mean that you cannot authenticate to a system unless you also touch a piece that is physically attached to your laptop or your computer. Google introduced this for all employees in 2010. And since then, Google had not had a single incident of successful password phishing because it's no longer sufficient. You can't log in with just a password anymore. You also need this hardware second factor. It is super powerful. And even today in 2026, I recommend to companies who want to have a strong security stance to use a hardware second factor for their employees to authenticate. Another invariant that I'm very, very fond of is egress control. With egress control, the idea is that every instance in production is allowed to egress to the internet only for specifically allow listed destinations. And my experience with that was when I was head of security at Stripe. There was the log4j vulnerability. It was disclosed on a Thursday. And I had decided to do a 3-day weekend of music production. And when I talk with people about it, they usually say, "Oh, Niels, I'm so sorry. That must have been a terrible weekend. You probably didn't get anything done." But it turns out I had a wonderful weekend of music production thanks to my great team at Stripe. They then put a debriefing meeting on my calendar for early Monday morning, and they said, "Hey, Niels, we ran this incident over the weekend, but it was all in hand, so we did not think that we needed to interrupt your weekend. And it was all in hand because we had rolled out egress control. And the log4j vulnerability required that in order to fully exercise this vulnerability, you needed to download a malicious Java class of the internet. But with egress control, you can't go to arbitrary destinations on the internet anymore, and you can't download this malicious Java class, and so that exploit couldn't proceed. And in fact, this is the shape for many externally facing vulnerabilities. They very, very often require a second stage payload. And if you can't download that, well, you can't fully exploit the vulnerability. Another favorite of mine is positive execution control. This is the notion that for your employees' endpoints and your production systems, only known binaries are allowed to run. And you often find that for social engineering attacks, somebody is trying to talk your employees into downloading a binary and running it to help with some kind of IT problem. Well, with positive execution control, this binary is going to be unknown and you can't execute it. These security invariants can live at every single layer of your stack. And Dino just pointed out to me the other day that memory tagging is a security invariant. The idea here is that you, for every pointer at memory, you associate a 4-bit tag. And now if you have a heap out of bounds write and you sort of try to write into the next allocation, if the tag doesn't match, your process is just going to get killed. If you are trying to double free a pointer, the tags don't match and your process is just going to get killed. And this is now deployed on modern Android phones and modern iPhones. In fact, if you use the operating system heap allocator and the right libc, this can get deployed to your binary without you really needing to make any changes at all. And there may even be an argument to be made that we should be leaning into these hardware capabilities also for our production deployments, because that might actually be easier than doing a software rewrite for everything. However, if we sort of back up to the highest level, I think most companies should really worry about insider risk. And for many, many companies, that is very challenging. The context-aware data access security invariance lives in the insider risk space. And the idea here is that you only get access to sensitive data if there is a business justification that can be verified a priori. If there is no business justification, no data access. For most companies, that comes in the shape of they have customer support. They often outsource customer support to third-party vendors. And in many cases, these tools tend to be broadly provisioned, and a rogue vendor might be able to access all your customer data. Well, with context-aware data access, you would do this differently. You would say, well, you get to access this customer data only if you are assigned a ticket for that customer, and otherwise you just don't get the access at all. Very, very powerful security invariant. There are a lot more, but that gives you sort of a sense of where the problem space lies. Unfortunately, in the past, I always said, well, these security invariants are nice. We have known about them for many, many years. We know that they're effective, but they're just not available to most companies. And they were not available to most companies because you needed to be a software engineering company. You needed to have an executive team that was aware enough to understand that the security invariants are important, that would be willing to prioritize it and to budget it. And then you also needed to be able to hire top-notch talent to get them implemented in your organization. And it turns out the software engineers with the knowledge to build these security invariants, they were in high demand, and most of the top tech companies were trying to hire them. So you were completely out of luck. Well, fortunately, that equation doesn't quite hold anymore. And in fact, these days with AI-assisted coding, you might be able to get away with just a very few software engineers to build some of these security invariants for you. And in fact, I do have this Iron Curtain workflow that is exactly around the design and code cycle. And I believe that I could build or write a specification for egress control that would allow a company to scope out their current production environment, figure out the best egress control solution, build that, incrementally deploy it, see that it works, and then end up enforcing it. And that, in my mind, is really sort of the hope that I see in the horizon and the future. And the takeaway that I would like you to have is, yes, we are now living in a world where 0 days are going to be created and found every single day. We are also living in a world where it's very unlikely that we will be eliminating all security vulnerabilities in the future. But if we heavily lean on these security invariants and we build infrastructure that enables them, we just can make a lot of these bug classes completely irrelevant and completely unexploitable. And that is really what I would like you to think about very carefully. To close this out, you can find Iron Curtain at ironcurtain.dev. You can find my findings about the data breaches and the invariants that would have prevented them at securityblueprints.io. And I would also like to point out the significance of April 7th. That was when Anthropic released their Red Team report, but it was also the 12th year anniversary of the OpenSSL Heartbleed vulnerability. And under Activate, we produce cybersecurity themed EDM to educate people about security. And on April 7th, we released a dance pop love song that celebrated the Heartbleed vulnerability. You can listen to it at activate.io/heartbleed. Thank you very much.